Welcome to the third lecture of the video lectures on theory of computation, hardness reductions from 3-SAT. In this lecture, we're going to be reducing from 3-SAT to Hamiltonian cycle. If we believe that 3-SAT is hard, this is going to show that Hamiltonian cycle is only a harder problem, and thus we must also believe that Hamiltonian cycle is hard. Let's just briefly recap the anatomy of a 3-SAT reduction. Again, 3-SAT is the 3-SAT problem is given a formula in conjunctive normal form. This is a and of or clauses, and we output yes if there exists an satisfying assignment of the variables that makes this formula true. What are our goals? What is a 3-SAT reduction trying to do? We're trying to show that a new problem y is hard by reducing from 3-SAT. Okay, so the key points of this reduction, again, we are trying to solve 3-SAT with a funny computer that has a built-in solver for our problem y, and in this case is going to be Hamiltonian cycle. Okay, and to do that, we need to use the constraints of problem y to ensure the constraints of 3-SAT. What are those constraints of 3-SAT? Those constraints are each clause has to have at least one representative true literal, and representative true literals have to be consistent, meaning you can't have two representative literals, showing that these different clauses are true if those two clauses correspond to the same variable and its negation. Those would be inconsistent. That would not correspond to a satisfying assignment. Great. And so let's look at the problem of this video, which is Hamiltonian cycle. So Hamiltonian cycle, we are given a directed graph on vertices and edges, and we are going to output yes if this graph contains a cycle that visits each vertex exactly once. Okay, this problem is a relative of the infamous traveling salesman problem. It's an unweighted version of the traveling salesman problem. Cool. Let's jump in. Okay, I've got my key points and constraints of 3-SAT iterated here. Let's start out as usual with part 1. And part 1 is our forward instance construction. Okay, and again, if we're in a 3-SAT reduction, we're always just trying to solve 3-SAT. So our input is 3-SAT. We're going to try to be converting it to an instance of Hamiltonian cycle. So our goal is to map that instance f of 3-SAT into an instance of the Hamiltonian cycle problem, which is just, we'll call it VF and EF, our vertices and edges of our directed graph. Okay, and we want, if 3-SAT is satisfiable, then this Hamiltonian cycle, this graph has a Hamiltonian cycle, and if 3-SAT is not satisfiable, this Hamiltonian cycle this graph does not have a Hamiltonian cycle. Okay, so again, what we always just have to do is go back to these constraints. Okay, so we're trying to solve 3-SAT. We need each clause to have one representative true literal, and we need representative true literals to be consistent. Okay, and somehow we need to map the use the constraints of Hamiltonian cycle, right? Each there's a cycle through the vertices that visits each vertex exactly once. We have to use this constraint exactly once, and it's a cycle to somehow get it to satisfy that each clause has one representative true literal, and representative literals are taken are consistent. So yeah, what we're gonna this is this construction is gonna follow a frequent template, which is that, well, again, I'm gonna have these literals represented by different um, you know different parts of my construction. I need to somehow make sure that every time I think about a literal, I think about it in the same way, and I can't take a literal and its negation into the 3 set. And so I'd like to represent that, each variable, when, uh, we have to choose that variable to either be true or be false. And if that variable is true, then the literals that it correspond to in the positive sense, those clauses can be made true by this variable. And if this variable is false, then literals that correspond to this variable in the negative sense, those clauses can be made true. So here's what we're going, and we need to do all this with a cycle in a graph. Okay, so cycles and graphs are a little bit confusing. I'm going to just do an example picture here. Okay, cycles and graphs are confusing, so I'm going to start out just by assuming I want a path. So I'm going to have an S at the top and a T at the bottom, and I'm just going to make sure that I can get all the way back up there. Okay, so well, imagine starting at S, and if we can somehow get to T, then we can wrap back around. It'll be a cycle. Great. Okay, and then what I'm going to do is I'm going to have rows corresponding to every vertex. Okay, so this is going to correspond to Z1. I'm going to have another row corresponding to Z2, all the way down to Zn. Okay, and here's the idea that we're going to use. Okay, so we're going to basically try to force the Hamiltonian cycle, if there is one, to walk through these horizontal vertices, either going all in one direction or going all in the other direction. Okay, and that's going to correspond to either the variable is true or the variable is false. And furthermore, we're going to force you to always walk in the same direction so that you can't, take the variable true some of the time and false some of the time, which isn't allowed at the reset. It's to be always true or always false. Okay, so I'm going to just show you what I mean here. I'm going to put directed edges going from, across, going one direction, and directed edges going back the other direction. Okay. And then I want to make it so that you can either take this in the forward direction or in the backwards direction. Okay. And so I'm going to allow you to go from S to either the left side or from S to the right side. Okay. And after you choose this variable, either going left or right, so we'll say going left is true, okay, and we'll say going right is false, okay. After we, pop down from S, we either go, the true direction or the false direction. We're going to allow ourselves to pop down to Z2, and we'll allow you to go either way. So you either can switch sides and go the other direction, or you can just pop down uh, and go in that direction. So you're sort of building the graph in layers, each time allowing yourself to pop down and or go across and go in the opposite direction. Okay, and this is just what's going to happen all the way down. Okay, and so this is sort of what I want to create here. And so far, what do we have? So far, we have a graph that, look, it's got a lot of Hamiltonian cycles, right? Because I can just take any variable any which way I want, and that's just going to be a path in this graph. Oh yeah, and when I get down here to n, I can just go to t and pop back up there to s. Okay, good. All right, and so what I want to do now is I want to introduce clause vertices. Okay, so there's going to be a clause vertex, which I'll call C1 through CM, corresponding to the M clauses. Okay, and here's the idea. If you're heading, imagine clause, we have that example where f of z is equal to, we'll say z1 or z2 or z3. And z2 bar, whoops, and z2 bar or z3 bar or z4 bar. Okay, so if this, what I want to do is I want to create these extra vertices out here, and if you're crossing z1 in the true direction, meaning going from right to left, then you can hop on over to C1 and pick up that vertex, because this Hamiltonian cycle has to go through every single vertex, so I must get to the C1 vertex. And if I'm going through this horizontal path in the true direction, I can pick up C1. If I'm going through the horizontal path corresponding to Z2 in the true direction, I can pick up C2. Right? That's what I want to create. But notice that if I'm going through Z2 in the true direction from right to left, then I'm not going from left to right. And so I can't, I want to make it so I can't pick up C2 if I'm going through Z2 from right to left. Okay, so how am I going to do this? So what we're going to do, and I need to, I guess, zoom in here. So let's zoom in on what's happening. Okay, so we have Z1. We have C2. And what we're going to do is with this C1, again, if we're going in the true direction, which is from right to left, we're going to allow you to pop over walking in that direction to C1. So I'm going to connect here and like here. Okay, and so what I want you to note is if you are walking through, if you're walking through in this direction, you can walk like this. Right, and you can just hop on over there and pick up C1. Okay, and likewise for C2. Uh, for C2, we're going to have it go the opposite way. So I want to make it so that if you're walking through this for C2, you can hop on over there and pick up C2. And so C2, I can pick up with clause 2, with Z2 in the false direction. So false direction is going from left to right. So if I'm walking from left to right, I can hop over to C2 and then hop back. And as I proceed in that direction, I can pick up C2. So that would be hopping this way, heading here, heading back, picking up C2 that way. Okay. Good. And so essentially, we're going to connect C1 is a clause with 3 literals. So I'm going to be connecting C1 in the same way to variables corresponding to Z1, Z2, and Z3. And I'm going to be connecting C2 in a similar way to the literals corresponding to Z2, Z3, and Z4, etc. And one thing that we're going to be concerned about is, well, maybe if we're not careful, we could be walking through the Z1 line. We could pop over to C1, but C1 is also connected to Z2. And then we could pop down to Z2 and walk down some Z2 line, right? And then we pop back to some clause and then eventually get back up to Z1 and then finish the Z1 line. So we got to make sure that this can't happen. And so how are we going to do that? Well, we're going to make it so that these lines are so long and straight that the only way you can get all the way through them is if you go all the way through them the first time. And so the way we're going to do that is just to blow up. So again, this is just to, make a method of what we're doing here. This is the overall picture. Okay, this is how the clauses are picked up. Okay, and now I want to say exactly how we make sure that we, respect this idea that we sort of go in order and we don't sort of, we can't hop back up in these rows. Okay, so I'll call that consistency. Okay, and the way we're going to do that is we're actually, when we make the ZI line, we're going to make it really, really long. Okay, in fact, the ZI line is going to be 3m vertices long. Okay, and it's 3m vertices long, so we can have basically designated spots for each clause that are going to skip a vertex. And by skipping a vertex, so in other words, it might look uh, like this for clause 1. It might look like this for clause 2. And maybe it looks like this again for clause 3. Okay, but I want to note that here's the key property of this. So we want to guarantee that basically, if you go somewhere, you have to come back. Okay, so in other words, if I'm, hopping along, if I'm hopping along here, and I happen to go collect this clause, I want to say that you have to come back. And why do you have to come back? Well, first off, at that clause, once you're there, you can never visit this clause again. It's a Hamiltonian cycle. Each vertex is visited exactly once. Okay? And so the only way to get to this edge, this vertex here, is if I come back to it. If I don't come back to it, I can't get there. And in particular, um, I need to come back to it right away. And remember, these edges looking like this. And the only way I can get to this vertex is if I come that way. Otherwise, notice that I'm gonna get stuck here, right? Because I can't, there's no way I can get in here to pick up this vertex unless I've come, from this direction from this clause, because I'm trapped. I've made myself sort of a dead end. Okay, so by spacing these vertices out, you make sure that you sort of have to go through these long rows corresponding to the vertex all in the same direction. Cool. So this is sort of, a hand wavy construction, but this is our construction. Okay, so we have paths. For variables, we have vertices or clauses. Okay, and the assignment of true or false to a variable corresponds to taking a path in one direction or another direction. Take path left. Okay, and zi is false means path right. Okay, we space out. These are paths of length 3m. So there's a spot for every clause to get picked up. And we have great. So that's a sort of a informal version of this construction. I think the pictures are intuitive and such. And if we were going to really complete this, which I'm not going to do here in this lecture, we would then have to do part 2 and part 3 of the construction, which are the backwards certificate and forward certificate construction. Okay, showing essentially that it's an if and only if, uh, that this Hamiltonian cycle, this graph has a Hamiltonian cycle if and only if the formula is satisfiable, and that boils down to showing that this path that we constructed, uh, first off, one direction is the forward direction is usually fairly easy because if this formula is satisfiable, then, sort of the path that we're imagining being taken actually is a Hamiltonian cycle in this graph. Okay, and that's the forward certificate construction, which is usually the easy direction, and then the harder backward certificate direction says that, well, and the big difficult part is the big difficult part is this consistency part, where we have to make sure that we don't have some wonky paths through this graph that are actually Hamiltonian cycles that don't actually correspond to taking the variables all in the same direction. Great. Okay, so that was our reduction from 3-sat to Hamiltonian cycle. So if we believe that 3-sat is hard, we have to believe that Hamiltonian cycle is hard. Up next, we're going to do the 3-sat to 3-dimensional matching reduction.